Hi guys, my name is Jeffrey A. I'm a DE student from San Diego, California. For my demonstration project, I'm going to be doing some demonstrations with a solenoid. And here goes. The magnetic field and flux density that is generated by a current-carrying conductor can be characterized by the Biot-Savart law, which is shown on the slide. But in real solenoids, the coils also vary with respect to solenoid radius A, making accurate characterization of a solenoid rather tedious. Overall, it's pretty hard to design an efficient solenoid, but in general, I found that you want these properties. Number one, you want high current. Number two, you want a large number of coils with minimal amount of air gap in between them. And number three, you want an armature with large cross-sectional area that fills up as much of the inner solenoid tube as possible. Hi guys, so what I have here is a simple solenoid that I built using some plastic pipe, some 20 gauge wire, and a 9-volt battery. And placed into the center of the solenoid is a steel bobby pin, which, for the purpose of this demonstration, it's a ferromagnetic material. Now let's see what happens when we hook the solenoid up to the power source. As you can see, the bobby pin went inwards towards the solenoid. Now, what would happen if we reverse the direction of current? So hi again, in my new setup, I've reversed the direction of current, so the wires are going to be going to opposite terminals on the battery. And again, let's see what happens to the bobby pin as I connect to the power source. We see again that the bobby pin tends to go inside the solenoid. And why is that? Well, it being made out of steel, it's a ferromagnetic material. As such, when I create a magnetic field with this solenoid, what happens is that the pin itself will always want to center itself so that its own poles are as close to the poles of the solenoid as possible. So whether the current is going one way or another, the pin will naturally want to move inwards so that the left side will align with the pole of the solenoid and the right side of the pin will align with the right side of the solenoid. And that's for a ferromagnetic material. So let's now go to another demonstration. So for my next demonstration, I want to show you a simple linear actuator that you can construct using a solenoid. Now in this case, I have a permanent Alnico magnet armature attached to the solenoid, and I'm going to use the solenoid to push this spool. So let me set it up. Okay, so there's the spool, and when I power up the solenoid, as you can see, it works as a linear actuator to push that spool. Obviously, you can use this very same principle to create and design a lot of other linear actuator type of mechanisms. So for my last demonstration, I want to show that you can use that linear actuator and convert it such that the linear motion is changed into rotational motion. So what I have here is a simple piston mechanism in which the linear actuator will drive, and attached to that mechanism is a cardboard wheel. So let's power up the solenoid. And let me reset the mechanism and do it one more time. So as you can see, I'm able to create some rotational motion, and you might even imagine that with a powerful enough solenoid and using a flywheel with more rotational moment of inertia, I might be able to create a reciprocating engine. Sadly, I don't have all the materials and tools necessary to build a solenoid engine, but the same principles would apply. So that's my demonstration. Thank you.